This conference will now be recorded.
Hello everyone, the topics we are going to discuss today, some important compounds of magnesium and calcium. So you can see all the compounds here, and after that biological importance of magnesium 2 plus 1 and calcium 2 plus 1, and there will be some related problems. So here you can see the first compound is magnesium chloride, only one magnesium compound is there, and then we have calcium related compounds, total 4. And cement is also there, though if you see the composition of cement, it's very versatile. But main component is CaO, that means calcium 2 plus ion is again present. So these are some important compounds of Mg and Ca. So next we'll first start with magnesium chloride. Now when it is anhydrous, the formula will be MgCl2, but if it is hexahydrate, then you have to write the formula like this, MgCl2 dot 6 water molecules. Okay, and how we can prepare it? So we will start with MgO, that is magnesium oxide, which is the source of magnesium 2 plus, and for chloride ion we will take hydrochloric acid. We are getting here the salt magnesium chloride along with water. The properties of this compound, as you can see here, it appears as white to colorless crystalline solid. Water solubility is very good, also in ethanol. And if you consider organic solvents like acetone and pyridine, now the solubility is obviously not good because it is after all ionic compound. So it is slightly soluble in acetone and pyridine. Strongly deliquescent in nature. So if you keep it open air, it will attract water. That is the reason it becomes the hydrated form MgCl2 6H2, and the name will be magnesium chloride hexahydrate. Being an ionic compound, its melting point, boiling points are very high, and aqueous solution if you take, or if you take the molten state, in both state it can conduct electricity because of free Mg2 plus ions. Now the uses of this molecule, magnesium chloride, it is used as a desiccant. Now desiccant means, suppose if you want to keep any chemical compound in dry condition, fine, in closed area, then there are some desiccants we use, some calcium compounds we also use, but magnesium chloride here, that is the application part we are discussing here. So you can use magnesium chloride as a desiccant so that it can absorb the extra moisture, because we have seen in the previous slide it has deliquescent nature. So because of this deliquescent nature, if we keep it in the area where we want the environment free from moisture, that is dry condition, then MgCl2 can be used because it can absorb the extra moisture from the environment, and you can keep other chemicals in presence of this MgCl2 desiccant because it will then remain in dry condition. Commonly used for dust control, road stabilization, because it has some special capability to bind ultrafine dirt particles together, and as a result creates hard surface. Now this hard surface is more stable than untreated roads and surfaces. It can be used to make magnesium metal itself, that is you have to use some reducing agent so that Mg2 plus ion will be converted to magnesium metal, that is the metallic state, or magnesium alloys, then magnesium, other magnesium compounds. So magnesium chloride, source of Mg, it can be used for electrolyte replenishment and conditions in our body which is associated with magnesium deficiencies. So electrolyte replenishment means there are some ions that are required for our daily basis, the bodily functions that are occurring. So Mg2 plus is one of those electrolyte ions which is required because there is some requirement in our body, and if there is deficiency, then to remove that deficiency we can use MgCl2 as a source of magnesium. Mixed with hydrated magnesium oxide, that is MgO in hydrated form, if we mix it, this MgO with MgCl2, then it forms hard material which is called sorrel cement. So these are the uses for MgCl2. Next compound we will go, which is calcium compound, calcium oxide. Now this is the actual name, but it is also known as quicklime, or sometimes we simply call it lime or burnt lime. So these are the different names we use. How we can prepare it? For commercial scale preparation, that is large scale, we can heat limestone. So as a source of calcium, we have taken here calcium carbonate, which is also known as limestone, in lime kiln, which is a apparatus where high temperature is used. Okay, that is known as kiln. In the temperature range, you can see the temperature is very high. So that is why this type of special apparatus is taken. So it is basically decomposition of calcium carbonate, and we will get our desired compound, that is we are trying to prepare, which is calcium oxide, and this is the byproduct. Now this reaction is reversible in nature, as you can see from this sign. So if you can remove this CO2, because it is the side product, if it is removed from the kiln immediately, then the production of CO will increase, and this is based on Le Chatelier's principle. Because according to this principle, if we remove the concentration of CO2, the equilibrium will be shifted from left hand side to right hand side. That means you will get more of calcium oxide. Okay, in this way we can increase the yield of calcium oxide. Properties: calcium oxide is white amorphous solid, not crystalline, amorphous. It is having melting point very high. So it is stable compound and it can withstand very high temperature. It can also absorb moisture on exposure to the atmosphere, and after absorption of moisture, the product that we are getting, that is basically calcium hydroxide. So based on this equation, CaO, one molecule of water, now we are getting CaOH whole 2. Now this is known as slaked lime, because we are getting it from lime or quick lime, so the name is slaked lime, and the process by which we are making slaked lime, that is known as slaking of lime. So as if we are feeding water molecule to calcium oxide, and we are getting calcium hydroxide. So calcium hydroxide is known as slaked lime, and the process is known as slaking of lime. And lime means calcium oxide. You can call it quick lime, lime, burnt lime, or simply calcium oxide. It can absorb CO2, which is basically the reverse reaction of this one that you have seen in the preparation part. So if you consider the reverse reaction, it can absorb CO2 when it is exposed to atmosphere, and it can produce calcium carbonate, which is also known as limestone. Now calcium oxide is basic oxide, and it has to be, because after all it is metallic oxide. So being basic oxide, it can combine with acidic oxides at high temperature and will form respective salts. So look at these three equations. When it is reacting with SO3, that is sulfur trioxide, we are getting calcium sulfate. So sulfate ion we are getting from SO3. Then another acidic oxide is silicon dioxide, because it is non-metal. Sulfur, silicon, these are non-metals. So that is why it is acidic oxide. We are getting calcium silicate, SiO3, 2 negative ion. This is the ion present in CaSiO3. Then with P4O10, so this is oxide of phosphorus pentoxide. Basically, it is the dimeric form of P2O5, P4O10. But ultimately, what anion we are getting? We are getting phosphate anion, Ca3PO4 whole 2. So phosphate ion is having 3 negative charge per PO4 unit. That means total negative charge PO4 whole 2. So total negative charge is -6. So that is why we have 3 Ca2 plus, because total positive charge will be 6 plus. So in this way, you can easily remember the formulas. Calcium phosphate. Uses of calcium oxide, as you can see here, how it looks. Due to its high melting point, calcium oxide is used as refractory material. Now, what is refractory material? It is something that can resist decomposition when it is facing heat or chemical attack. So even in presence of high heat and chemical attack, the material will not be decomposed. It is resistant to decomposition. So as you have seen in the properties part, that calcium oxide is stable compound, melting point is very high, so it can withstand high temperature. So that is why it can be used as refractory material, because you just use any material for the purpose of refractory material. It has to be such which can resist decomposition by heat and chemical attack. So CaO is one such material. It is used in the manufacture of cement. So when we will actually discuss cement, you will see its composition. Calcium oxide is basically the main part. Then sodium carbonate preparation, that is Na2CO3, starting from caustic soda. Some dye stuff, raw materials such as paper, steel, etc. Purification of sugar, in that process also calcium oxide is useful. Medicinal purpose there is used, as well as for the development of some insecticides and pesticides. Widely used in laboratories for chemical processes where precipitation is required or dehydration is required, because this molecule CaO, it can absorb moisture. That means it will help in dehydration. Then calcium oxide, upon further reaction, it can also be the source of other calcium compounds. So these are the uses of calcium oxide, or quicklime or burnt lime. Next calcium compound is CaOH whole 2. So you have already seen CaOH whole 2, and if you look at the equation for its preparation, this equation we have already seen in the properties part of, remember, in the properties part of calcium oxide we have already seen this reaction, and that is known as slaking of lime. So slaking of lime basically we are using for the preparation of calcium hydroxide, and remember it is also known as slaked lime. Another method is, if you treat NaOH with calcium chloride in water medium, then also we can get calcium hydroxide, and sodium chloride will be the byproduct. Properties: white powder, sparingly soluble in water. So water solubility is not good. Now look at these terms and be very careful, because these terms are very close to each other, but they are not same. It is true that it is sparingly soluble. Solubility is not good, but that is the portion where it is actually soluble. That is, after dissolving it, there will be, you can see some amount is not yet dissolved. So you can filter, and the transparent liquid that you will get, that is the amount of the solution where it is actually soluble calcium oxide, where it is hydroxide, where it is soluble. That aqueous solution is known as lime water. So the aqueous solution of this compound is lime water. But if you consider the suspension, that is where still you can see some white powder, it is suspended condition, then that suspension you will call slaked lime in water. Suspension of slaked lime in water means suspension of calcium hydroxide in water. That is known as milk of lime. So you can use this term milk, because when we are saying milk of lime, means it is not transparent. There is some whitish appearance. So that is why we are calling it milk of lime. It is suspension. It is not clear solution. But the clear part is known as lime water. When melting point temperature is approached, then it tends to lose water and there will be decomposition. If you are treating it with carbon dioxide, so see how it is written here, when CO2 is passed through lime water, that means you are passing CO2 through the solution of calcium hydroxide, then it turns milky because of formation of calcium carbonate. Now this observation is used to detect whether you have any CO2 gas present or not. Suppose you are doing any reaction where CO2 gas is liberated, and you want to check whether this liberated unknown gas, whether it is CO2 or not. Then what you can do, you can pass this unknown gas through the solution of CaOH whole 2, that is through lime water. So if it turns milky, it proves that CO2 is present. And another process you can also do after doing this, which is the first equation, CaOH whole 2 plus CO2, you are getting CaCO3, and that is why it is appearing as milky suspension. But if you pass now excess of carbon dioxide, now this precipitate calcium carbonate, it reacts with CO2 and water and ultimately forms calcium bicarbonate. So the formula is now CaHCO3 whole 2, because HCO3 is having only single negative charge. So you need two of these anion. So that is why the formula is CaHCO3 whole 2. Now this molecule, that is calcium bicarbonate, it is not like CaCO3. So when it is CaCO3, there is some milky appearance, but if you pass excess of CO2, this precipitate of CaCO3 dissolve and ultimately you get calcium bicarbonate. So the milky appearance, that will no longer be there. Okay, so in this way we can prove whether CO2 is present or not. Properties: calcium hydroxide reacts with chlorine. Now this is very important reaction, because in this way we can produce this compound which is constituent of bleaching powder. So calcium hydroxide reacting with chlorine and we are getting calcium chloride salt, another salt which is the constituent of bleaching powder, and water is the side product. Now to the application part. Calcium hydroxide used in industrial settings such as sewage treatment, paper production, construction, food processing. Then to prepare lime mortar, which is actually a building material. Pesticide hair care products, manufacture of ebonite, which is a special kind of rubber. Then in root canal process, this compound is used to fill the cavities in the human teeth. Then in tanning industry, glass making, preparation of bleaching powder, which you have already seen in this equation, and in the purification of sugar. So CaO also we have seen in the application part, it is used for the purification of sugar. Here also you are seeing the same thing. So here we have a problem which is related to the equation you have just seen. Though there is one more equation that also we have to solve. In the following reaction, products A and product B respectively, we have to choose. So first reaction, NaOH, hot and concentrated. Now mention of this hot and concentrated is important, because if you have taken NaOH, suppose you have taken dilute solution or cold solution, then you are treating it with chlorine, then obviously the products are different. So that is it is specifically mentioned, hot and concentrated reacting with chlorine, we are getting A, and there are some side products. But this is important because that we have to find in the option. And in the second reaction, calcium hydroxide dry condition reacting with chlorine. Now this reaction we have just seen in the previous slide in the properties part of calcium hydroxide, and remember there is formation of three compounds, CaCl2, CaOCl2 and water. Now we have to check the options because we have to find A and B. So the first compound NaClO3 in option 1 and 3 and NaOCl in option 2 and 4. And come for B, this is A, this is B. So all these are A and the second compounds are B. CaOCl2 and CaClO3. But it is actually CaOCl. So we can cancel these two. Now what is the product A? Now we will see the actual equations. It is not important to balance. Even if you just know what are the products, that is enough. Now in the first equation, this will be treated as side product. And here this will be treated as side product, because if you consider sodium chloride as the main product for reaction 1, sodium chloride is not present in the options 1, 2, 3, 4. And if you consider calcium chloride as the main product, that is if you consider CaCl2 as B, that is also not present in the option. So that is why focus is on NaClO3 and CaOCl2, because that are only mentioned here. Okay. So NaClO3, CaOCl2, option 1 is matching. So this will be the correct answer. Some more calcium compounds we have to see. We have already seen CaO, CaOH2. Let's now see calcium carbonate, which is also known as limestone. For its preparation, we will use the source of calcium, which is CaOH2. Now this equation we have already seen. Remember, if you pass CO2 gas through lime water, you get some milky appearance because of CaCO3. So this equation we are now actually using for the preparation of calcium carbonate. So when CO2 is passed through slaked lime, that is basically nothing but calcium hydroxide, and we are treating it CO2 and CaOH2. there is milky appearance, which is basically calcium carbonate along with water. One more method, calcium chloride as a source of calcium ion, and sodium carbonate, which is the source of carbonate ion. So here exchange of anions will be there. Chloride ion will be going to sodium plus, and calcium carbonate ion will be coming to Ca2 plus. So as a result, we are getting CO3 and sodium chloride. Properties, how it appears, it is white insoluble powder like substance. So water solubility is not good, so that is why we are seeing some milky appearance in this first reaction. So it is not soluble. And this powder like substance occurs naturally in minerals, chalk, marble, limestone, calcite. So that is, it is called limestone, shells, pearl, etc. Decomposition of calcium carbonate, we get CaCO3 and CO2. Decomposition at 1200. Now reaction with dilute acid. So which dilute acid we have taken? We have taken hydrochloric acid. So this carbonate ion, now it will be replaced by chloride ion. So we are getting calcium chloride. And the fate of CO3 is that now it is converted to carbon dioxide gas. If we take H2SO4 in dilute condition, then Ca and SO4 together will make calcium sulfate, and this H2CO3, it will not remain as H2CO3 because carbonic acid it is always in decomposed state. It will form water and again carbon dioxide. So these are the properties. Calcium carbonate, directly it can react with dilute acids, and it accepts the anion that is present in the acid. If it is HCl, it is chloride ion. If it is H2SO4, it is sulfate ion. Application. Medicinally used as an antacid, and that you can understand the explanation, because antacid means it can react with acid, excess acid in our stomach, and that is why we are taking it when there is excess acid production, because it can react with acid. In stomach there is basically hydrochloric acid, so it can react with HCl and producing CaCl. So that is why it can be used as antacid, and also as calcium supplement. So if we have deficiencies of calcium in our body, it can be the source of calcium 2 plus ion. Used as a filler in cosmetic, in the manufacture of paints, paper, plastics. Fertilizer to provide calcium to plants. Just we take it as a supplement. For the plants also it is required, and it is given in fertilizer. And for the pH stabilization of the soil. Soil, there should be a particular pH should be maintained for the plants, for the growth of plants properly. So for this stabilization of pH also, CaCO3 has some role. Extensive uses in the manufacturing industry as a building material, mainly the marble. Probably you have heard it. Then ingredient for quick lime and also cement. So in cement, when we will discuss it, you will be able to see that this is also present. Now, if you look at the options, quick lime, slaked lime, lime water, all the closely related terms, all are present together. So if you solve this question, you will be having some clarity. So see, it is saying that lime means CaO, reacts exothermally with water. So there will be for liberation of heat. It is giving A. So CaO plus H2O, we are getting some compound A, which has low solubility in water. Now aqueous solution of A is used for test of CO2. That means when you treat A with CO2, it is a test in which insoluble B is first formed. So insoluble B is first formed, and if you treat it, that is if you treat B with extra CO2, then soluble compound is formed. So some extra CO2 now you are treating it, and there is some soluble compound. But it is asking what is A. So see, It is very easy to answer. CaOH2, it is a combination reaction. It will be only one product. If you simply combine CaO and H2, it is CaOH whole calcium hydroxide. But in options, the formula is not given. So you have to know the term for it. Is it quicklime? Suppose you know that A is calcium hydroxide, but is it, how we call it? Is it lime water? Is it quicklime? Is slaked lime? It is actually slaked lime, because we get it from lime or quicklime by when quicklime absorbs water, and this process is known as slaking of lime. Now all the reactions you can see, calcium oxide, which is basically quicklime, then it is producing CaOH whole 2, which is A. It is not having very good solubility, but its solution, that is clear solution, is known as lime water, which is in option 3. But that is not correct, because it is not asking the solution of A, what we call it. It is simply asking what is A. So it is directly this compound, and that is known as slaked lime. This slaked lime, when we treat it with CO2, first there is milky appearance of ClCO3, but if you treat this B with excess CO2, now there is soluble compound calcium bicarbonate. Okay, so this is A, and this is also known as slaked lime. Sorry, this is the correct answer. Slaked lime. Okay, quicklime is CaO, and lime water is solution of CaOH2. But actual name, another name that we use for CaOH2 is slaked lime. The next calcium compound is plaster of Paris. Look at the formula. Calcium sulfate dot half water molecule. Now this is very unique. If you change this half to some other value, it will no longer be plaster of Paris. So only when you write half water molecule for one molecule of CaSO4, then only it becomes a formula for plaster of Paris. So how we can prepare it? We can prepare it starting from by heating gypsum. Now the formula for gypsum, it is also just like plaster of Paris, but look at this value. Now it is 2 water molecule per CaSO4. So it is different. When number of water molecules you are changing, the compound itself, its name is also changed. At temperature 373, 393, if we heat it, we lost water molecule. So see, CaSO4 2H2O, and half water molecule means 2 minus half, 3 by 2, that will be left. So 3 by 2 water molecules removed. So this is plaster of Paris. Properties. Now this is having a very unique property, and that property is in presence of water there is some setting occurs. When water is mixed with dry plaster of Paris, CaSO4 half H2O, there is some restructure occurs, okay, and it forms again gypsum. So as if it is again taking water and it is forming gypsum. Now as for the process of hardening and setting, sorry, there will be half and this will be 3 by 2. So as if it is the opposite reaction we are doing. It starts around 10 minutes. So this process of setting with water, so gradually it will be, there will be some hardening process occurring, but it will take some time, around 10 minutes. Plaster of Paris forms anhydrous calcium sulfate. So if you heat plaster of Paris at this particular temperature 473, then it loses these half water molecules. So once it loses these half water molecules at 473 Kelvin, we get calcium sulfate molecule without any water. It is anhydrous, and that is known as dead burned plaster of Paris. Now if you know the formula plaster of Paris, half water molecule is there. Now when we are using the term dead burned, that means there is no longer any water molecule. It is burned. You have heated it. So that is why the name for anhydrous CaSO4 is dead burnt plaster of Paris. And the temperature is 473. If you use lesser temperature, it will not happen. Only at particular this temperature only this half water molecule can be removed, and we can get anhydrous calcium sulfate. Then uses of this molecule, the largest use of this molecule is in the building industry as well as plaster, because it has some setting properties. One of the main use is to make cast for statues, molds, also in ornamental casting. Immobilizing the affected part of organ. So we all have seen it, but there is a bone fracture or sprain. So the plaster that we use, that is nothing but plaster of Paris. In dentistry also, this molecule is utilized for making a replica of oral tissues and teeth. It is used to make fine artwork for decoration, beautification of monuments, buildings. Then fireproofing products, that also we can make. Fire protection system also make use of this compound. Now here, though we have not discussed separately gypsum, but as you have now seen the formula for gypsum, because we have used starting material gypsum for the formation of plaster of Paris. So that is why we are also discussing the uses of gypsum, because you can get problems based on this. Crude gypsum is used as fluxing agent, fertilizer, filler in paper, textile, retarder in Portland cement. So we will also see its use in the cement topic when we will discuss only after this finishing this part. So there also you will see gypsum is also used in Portland cement for specific reason, because it has some retarding property. Around 3/4 of total production of this molecule is calcined for used as plaster of Paris. That means 3/4 of total gypsum calcine means it when you heat it at very high temperature to remove water partially or completely, that process is calcination, or the verb form is calcined. Okay, so gypsum is used for production of plaster of Paris. An equation you have already seen how from gypsum we can get plaster of Paris. And as building material in plasters, some specific name you can see for cement, board product. Now this application is important. Board product means it may be plaster board, drywall or wall board. That is the electric switch board that we use. There also it has some use, and it is because of some special fireproofing property it has. So that is why you can use for formation of board products. Okay. So see, now we have this problem which is related to gypsum. Two statements we have, assertion and reason. And assertion is saying that gypsum is used for making fireproof wall board. So in the last slide you have seen for board product. That is the overall term we have used, and under this board product, as you can see here, it is mentioned board product. It may be plaster board, drywall, wall board, anything. So this statement is actually true. We have seen it in the application part. Gypsum is unstable at high temperatures. If you heat it, obviously there is some change in the water molecules. You have seen how we can get plaster of Paris. So we cannot say it is stable at high temperature. So it is unstable at high temperature. So this is also true. But the next question is, both are true, fine, but is it the correct explanation for which we use it for board product, fireproof wall board? Actually, that is not the case. It is indeed used for making fireproof wall boards because it is having some fire resistant property. It doesn't support combustion, doesn't emit toxic fume when exposed to fire. So that is why it is very good for using this type. That is the purpose we can use. Our purpose is to make fireproof wall board. So obviously we need something fire resistant. It is not that it is unstable at higher temperature. That is not the reason we are using it. The reason is it is fire resistant. That is the actual explanation, right? So both are correct, but we cannot say that reason statement that is given in the problem, it is not the correct explanation. The correct explanation is mentioned here. It is different reason. Problems related to gypsum again. Here we have in the central position, gypsum is mentioned. Look at the formula, 2H2O, and gypsum is already written. Now you are heating it at 120 degrees centigrade, you are getting A. When you are heating it at 200 degrees centigrade, that is you have increased the temperature. Now when we have discussed plaster of Paris gypsum, actually the temperatures we have mentioned in Kelvin. but see here it is centigrade. So don't be confused between centigrade and Kelvin, because problems there may be mention of centigrade as well as Kelvinos. Okay. So when 120 degree it is A, when 200 degree that is greater than this temperature, high temperature, then there is different product. Now this different product, when you are further heating very strongly, there is formation of C. Now when it is 120 degree centigrade, if you look at the options, there are total 3 names given. So the first one is A, because it is mentioned ABC respectively. Second one is B, which may be dead band plaster, plaster of Paris, dead band plaster again, and plaster of Paris. 2 options are there for C. For B. And for C, it may be calcium sulfite, then lime, again calcium sulfite. And for A, 2 options, plaster of Paris, okay. B, we have dead band plaster and anhydrous calcium sulfate. Now look at this equation. If I am writing it number 1, this is number 1. It's number 2, this is number 3. So when equation number 1, when you are heating it 120 degree, you can also convert it to Kelvin. Then there is basically 3/2 water molecules removed. That means you are getting plaster of Paris. This is the formula, plaster of Paris. So B and D we can cancel. It has to be any one of A and C. Now A and C, the second one is also same, only the last one is different. Now when you are heating it at 200 degrees centigrade, now the compound is basically complete loss of water, because now the temperature is high. So complete loss of water, this is known as dead band plaster. Remember, this term we have already used. And when you heat calcium sulfate again, what will be the number 3 equation? When you further heat it, it is decomposed to SO3. SO3, and 1 oxygen will come to calcium and it will be calcium oxide, and this is nothing but lime, or it can also be called quicklime, but in the options it is simply mentioned as lime. So correct one will be option last, C will be the correct option, right? So POP, that is I mean to say plaster of Paris. There is dead band plaster. This is A. Dead band plaster is calcium sulfate and hydroxide, and lime is calcium oxide. Okay. Now the last one for important compounds of magnesium and calcium. This is the last one. Cement. Now cement, first of all, you have to understand its composition. Though it may vary, but more or less, what are the basic composition that you have to understand for Portland cement? It is obtained by combining a material which is rich in lime. So this is the main composition. And there will be some other materials also, such as clay. Now clay contains silica and along with oxides of aluminium, that means Al2O3. It may be an oxide of Fe. It may be oxide of Mg, that is magnesium oxide. Okay. Now you can see the percentage. Lime is the main percentage. Then magnesium oxide 2 to 3, silica is there, ferric oxide Fe2O3, iron oxide, aluminium oxide, and oxide of sulfur. Now for good quality cement, there is some specific ratio we maintain. There is a ratio of silica, that is SiO2, this one, and aluminium, this 5 to 10%. This ratio should lie between 2.5 to 4, and the other ratio, that is lime to total of silica, alumina, ferric oxide, should be as close as possible to 2. So lime, the ratio of lime to this. So you can see if it is, we are saying that is 2. So the ratio of lime divided by silica, alumina, I'm writing simply as A for alumina, then A for ferric oxide. So all these together, then it is 2. That means you can understand that this is obviously present in higher percentage. Then only you can get ratio like this. So these are the more or less average composition. So cement is used as an important construction material. We know that it is essentially a finely powdered mixture of calcium silicate. Though here calcium silicate is not mentioned, but if they react with each other, there is formation of calcium silicate, that is SiO3 whole 2, and calcium aluminate also, along with small quantities of gypsum. Remember in gypsum, that slide I have mentioned that sometimes gypsum is also added to Portland cement for specific purpose. So ultimately, it sets into hard stone-like mass when it is treated with water. Fine. Now, look at the raw material that is required if we want to manufacture cement. Raw materials are limestone, calcium carbonate, clay, where main composition is silica alumina, and gypsum is obviously required. So small amount of magnesia and iron oxide. Magnesia is nothing but MgO. Fe2O3 are also required for imparting suitable color. So manufacture of cement, the steps that we follow for its manufacture is, we have to take limestone, that is calcium carbonate and clay, in this particular ratio. So the first two compounds in this particular ratio we will take, then heated in rotary kiln is which can withstand very high temperature. Look at the temperature, it is very high. Then after heating, there will be some decomposition of calcium carbonate. Now you are getting this quick line. In the previous slide, we have seen the average composition where you can see 50 to 60% is CaO. It is a final average composition. But when you will actually make, that is manufacture the cement, then you start from calcium carbonate and clay. So you have taken it in 3:1 ratio and you are heating it in kiln at this temperature very high. So the processes that occurs here is decomposition of CaCO3. Now you are getting this calcium oxide. Now this line which we obtained after decomposition of limestone, alumina, silica react with this. Now silica is already there in which is present in clay. So silica when reacts with CaO, there is formation of CaO dot SiO2. You can also write it like this, SiO3. Like this also you can write, but it is written in this way, CaO dot SiO2. Then calcium oxide reacting with oxide of iron as well as aluminium, and it is forming this type of composition, CaO dot Al2O3 Fe2O3. You can also call it calcium aluminate if you are omitting Fe2O3. But whatever it is, exact composition we know we do not require. More or less try to remember what is the main part of cement. It is CaO, and there are some different percentage other compounds are present, and the percentage are clearly mentioned in the previous slide. Okay. Now because of these very high temperature in the kiln, 20 to 30% mass melts and combined with solid mass to form some pebbles, and these are known as cement clinkers. The hot clinkers are cooled and mixed with 2 to 3%. Now gypsum. Okay. Now the purpose for adding gypsum, it is basically slows down the process of setting with water, because if it is not slow, if it happens very quickly, there will be problem in other processes. Okay, that we'll see. But we have to add 2 to 3% gypsum to retard the setting process. And finally, we get finely powdered mixture, which is Portland cement. Okay. So setting of cement. So once you have prepared it, next is the important constituent present in Portland cement. We have seen dicalcium silicate, Ca2SiO4, tricalcium silicate, tricalcium aluminate. Now, setting of cement, it is basically the hardening of the cement or stiffening of the cement from fluid nature. Now it will be rigid. So stiffening of the cement paste after water is mixed. Now why it is so? why it happens? It is because of the hydration of the molecules of the constituent. So it absorbs water, hydration of the molecules. There is some rearrangement, and it is exothermic process. Heat is generated. Why gypsum is added? To slow down the setting of cement so that it gets sufficient time before hardening. Okay, and the cement reacts with water to form a gelatinous mass, and then there is slow setting into a hard mass. Now, why it is becoming hard? Because of generation of three-dimensional network structure. So SiO-Si, this type of linkage is there. Now, in detail, this type of chain of SiO-Si that you will learn in group 14, P block. Because silicon is from group 14, there you can see the details of this structure, but it is having some network type of structure. So that is why it becomes hard, because of these SiO-Si or SiO aluminium chains. It is used in concrete and reinforced concrete. So obviously it can be used as concrete because there is some hardening. And what is reinforced concrete? See, when there is some iron structure like this, so these are iron rods, and then you are adding the cement. So it is basically reinforced concrete. There is some additional structure we are adding, and used in plastering. Then in construction of building, bridges and dams. So if you do not use gypsum, it will be so hard that we will not get enough time to spread this cement over these rods. So that is why gypsum is required, so that it actually takes some time to become hard. Otherwise, if you add water and then suddenly it becomes hard, it will be difficult to maintain all this process. So that is why gypsum is added to make this process slow. Now we have the same question that we are just talking about. Gypsum is added to cement because it makes cement very hard, increases pace of cement setting, slows down the initial setting of cement when water is added. So this is actually the correct answer, that is C. It controls the setting of cement. If you do not add it, cement will set immediately, leaving no time for concrete placing. So in reinforced concrete, you have to spread it over the rods. So it needs some time. So C is the correct option. Next question is also related to cement. Portland cement contains X to enhance the setting of time. So C, it is basically saying to retard the process of setting of time. That means it will enhance, it will increase the setting time. So what is X? So it is nothing but gypsum. Okay. And what is the formula for gypsum? It is CaSO4 2H2O. So this should be the correct option. Okay. Match list 1 to list 2. So now we have already finished different compounds of calcium. We have to match it. So antacid, remember, it is related to D. So if D is 1, you can cancel these two. And this is very unique formula. We know it is for plaster of Paris. So B should be related to 4. So option 3, it indicates. Then cement, bleach, you know, this one is bleach. That is the composition. And cement, the main composition, if you see, 50 to 60% is calcium oxide. So C is 2, B is 4, A is 3, D is 1. So this should be the correct option. The number of water molecules in gypsum. So with calcium sulfate, there is 2 water molecules. In dead burn plaster, there is 0 water molecule. For gypsum, it is 2. So 2020, that means these 2 you can cancel. And plaster of Paris, this is basically half, that means 0.5. So 2, 0, 0.5, the number of water molecules present in these 3 different calcium compounds. So option D is the correct option. Now the last topic we are left with, biological importance on MgSCA. Remember in group 1 also we have seen the biological importance of sodium, ion and potassium ion. So similar type of importance we also have for Mg2+ and Ca2+. Typical adult human body contains about 25 gram of magnesium, 1200 gram of calcium. It is larger, and the daily requirement is estimated to be 200 to 300 milligram. Now first we'll see the importance of magnesium. It is important constituent of chlorophyll pigment in plants, which initiates the photosynthesis process in green plants. So if it is not present in chlorophyll, that is chlorophyll, if it is not present, photosynthesis is not possible. Then these ions more concentrated in the intracellular portion compared to extracellular fluid if you consider animal bodies. Then it is required for activation of phosphate transfer enzymes which participate in the energy releasing biochemical process occurring in animal body. So it helps in the activation of phosphate transfer enzyme. So for activation of this specific enzyme which transfer phosphate unit, Mg2+ is required. It is also essential for DNA synthesis, responsible for stability, proper functioning of DNA. Important for carbohydrate metabolism. One of the important minerals to maintain healthy electrolyte balance in our body. Remember when we have discussed MgCl2, there we have seen in the users part that it can be used to remove the deficiency. So it is required in our body for electrolyte balance, and as a source of it, MgCl2 can be taken. If there is deficiency, it will lead to improper functioning of sodium potassium pump. So primary idea we have seen, that is primary idea of this sodium potassium pump we have seen in group 1. So magnesium 2+ also it has some role. If it is deficient, then this pump cannot work properly. What about calcium? 99% of body calcium is present in bones and teeth. So that is why its requirement is so high. In the previous slide, you have seen 1200 gram of calcium. That is the present. Okay. So it is because of this bone and teeth. Enamel on teeth is a double salt of calcium. So this is the formula for the enamel present in teeth. Then calcium concentration in plasma. It is regulated at about 100 milligram per liter. So in plasma of blood, because blood is not only, that is if you consider its composition, there is RBC, red blood cell, white blood cell, there is plasma. So we are now talking about plasma part of the blood, where calcium concentration you can see per liter it is 100 milligram. It should be the required amount. And this concentration is maintained by a specific hormone which is known as calcitonin parathyroid. So these hormones control this concentration. If there is deficiency of this ion, there will be blood will be taking longer time to clot. So suppose if there is some bleeding and if there is deficiency of calcium 2+, if clotting is not occurring at a proper time, bleeding will not stop. So clotting is very important, but for clotting to happen, we also need proper concentration of Ca2+. It should there should not be any deficiency. Also plays important role in neuromuscular function, interneuronal transmission, cell membrane integrity, blood coagulation. So blood coagulation in the previous point we have seen. Then in case of plants, there is significant role in the metabolism of nitrogen. So this is all about calcium, but in common way, if we consider the role of these two ions, then both these ions vital for transmission of electrical impulses along the nerve fiber and for the contraction of muscle. Here we have a question related to this, whatever we have just discussed. Element playing significant role in neuromuscular function, interneuronal transmission. So we have just read it, right? Interneuronal transmission, neuromuscular function. So obviously these two you can cancel, but there is a high chance to be confused between these two. So that is why I have mentioned the biological importance, magnesium separately, calcium separately. This part is common, but if you consider the separate points for calcium individually, for magnesium individually, then it matches with calcium, not magnesium. Though these terms are very close to each other, but see, neuromuscular function, interneuronal. It is true, these are related to biological terms. Details it is not possible for us to know, but for application, that is biological importance part. To answer this question, we have to know these terms. So here specifically this is mentioned, these two terms, which is already you can see here. So it is calcium, it is not magnesium. Okay. Two statements we have. The first statement is saying that an alloy of lithium and magnesium, you know, alloy is there where one component must be metal, another component may be metal, or it may be non-metal. Alloy of lithium and magnesium is used to make aircraft plates. Second statement is saying magnesium ions are important for cell membrane integrity. Now you have a look in the previous slide. Here you can see cell membrane integrity, it is for calcium, it is not for magnesium. So the second statement is false. What about the first statement? If you want to know the first statement whether it is correct or not, you have to just check in the uses part of group 1 elements, lithium, sodium, potassium. Uses part separately we have seen. Initial classes you can check, and the application part of group 2 elements, that is magnesium, calcium. So that is, if you just have to check in lithium and magnesium application whether this statement is correct or not, because several types of alloy is possible. Lithium, it can make alloy with Pb, that is lead. It can make alloy with aluminium, with Mg, but is it used for making aircraft plates? Actually it is not. Alloy of these two together used to make armor plates, not aircraft plates. So details you can find in the application, that is the users part of these two specific groups elements. So kindly check there. And calcium 2+ ion is basically responsible for cell membrane integrity. So both are false. So both statement 1 and 2 both are false. Okay. So that's all for this class, and also this chapter we have completed with biological importance of calcium and magnesium. So we'll end the session here. Thank you for listening.